She will be talking about multimodal proximity and visuotactile sensing with a selective transmissive soft membrane.
Hi everyone, my name is Jessica Yin and I'm a second-year PhD student at the University of Pennsylvania working with Dr. James Pikul and Dr. Mark Yim. So let's get started by watching everyone's favorite soft robot from pop culture, Baymax, as he tidies up this room. In many ways, I think Baymax represents the future that many of us here are working towards, which are soft robots that seamlessly integrate into human-centered environments and help people with their everyday lives. Just in this short clip, Baymax has managed to accomplish many technically impressive manipulation tasks that a lot of roboticists are still working on today. So let's break some of those tasks down. The first one, by Baymax using a broom, he shows mastery of tool use and spatial force and contact force regulation. By throwing these tools into a drawer, he shows that he can do dynamic tasks and trajectory prediction with the bonus of some multi-agent collaboration with the cat. He can also push and balance these books on a bookshelf, handle articulated and irregular objects, and manipulate deformable materials, as he does by folding these clothes. And these interactions are very challenging because they require really good perception of the target object, because they lack simple and accurate contact models. And I would argue that many of these tasks are still so challenging for a lot of roboticists today because we need much better sensors for manipulation, beyond the usual configuration of tactile sensors in the end effector and vision sensors much further away that are not very precise and easily occluded. So let's go over some recent progress in soft sensing for manipulation. I'll start off with Visuotactile sensors. So Visuotactile sensors use an embedded camera to measure the deformations in a soft surface as an object comes in contact with it. And cameras are really great for this because they have such high spatial resolution to capture that high dimensionality of deformations of the soft material. And so you can interpret those deformations for information about the target object, like forces or localization. We also have proximity sensors, so you can see this kind of array of sensors here, which kind of tries to mimic the same spatial resolution as a camera, but the form factor of these individual MEMS sensors requires a lot of wiring and kind of this like large format, which prevents the spatial resolution that we see with cameras and that spatial resolution that would be needed for higher level tasks like object recognition and tracking. Then we also have Visuotactile and proximity sensors, but the state-of-the-art sensors, they still have a fundamental compromise between the tactile and the proximity sensing modalities, a compromise in spatial resolution. So you can see here how these dots that are used for tactile sensing completely occlude the proximity vision, so you always have to kind of choose between one or the other. And so you might be wondering, why do we even need proximity sensing? Because tactile sensing, especially soft tactile sensors, have already been widely accepted into the larger robotics community. And I would argue that because we still struggle a lot with dynamic and dexterous tasks, that we actually have a fundamental gap in a perception pipeline that only uses vision and touch. I think we need to add proximity sensing. And I would define proximity sensing as a short distance range sensing originating from the locations of the tactile sensors. And proximity sensing can provide the precise localization data that vision sensors lack, or cover the occlusions that vision is usually easily occluded by, and also information about pre- and post-contact behavior that is not captured by tactile sensors that we don't have good models for. So the work that I'll present today is a novel multimodal proximity depth and tactile sensor. So we have an RGB camera inside that senses the soft membrane for tactile data, and then we have an infrared depth camera that gives us proximity data by looking through the membrane. We have minimal to no interference between both proximity and tactile modalities, which gives us uncompromised spatial resolution. And we also have simultaneous and synchronous proximity and tactile sensing for the development of sensor fusion algorithms. So when we think about cameras, they're actually really just really fancy light sensors. So what we do to enable these dual modalities is focus on the optical properties of the soft membrane. So our first goal is to have it be infrared transparent, which allows the infrared light emitted by the depth camera to pass through. And so that's how we get our proximity sensing modality. Our second goal is to block visible light from the external environment, and that allows us to observe the membrane with the RGB camera. And our third goal is to have this high contrast pattern on the membrane that we can use to track deformations with the RGB camera. So when we think about how do we create these optical properties of the membrane, the most basic question that we ask first is how does light transmission work? And essentially at the atomic scale, we have photons that come in and collide with these atoms, and the photons, they carry energy, and they can excite these electrons to higher and to discrete and well-defined energy levels. And if the photon is absorbed, then the light is not transmitted. But if the photon doesn't exactly have the right energy level, then that is transmitted. And at the material scale, instead of having these sharp peaks that we would expect to see from the discrete and well-defined energy levels that we see in atoms, the transmission frequencies actually broaden and become more continuous. So instead of seeing really sharp peaks, we kind of have a more continuous curve here. And our next question is, how can we get a high contrast visual pattern without interfering with proximity sensing? And this is kind of where understanding how light transmission works comes into play, because we are really only working over this really small range of wavelengths of light. And the infrared light that the depth camera uses is right next to the visible light range, which gives this challenge of that the excitation frequencies of visibly colored materials tend to extend into the infrared spectrum and block the depth camera. And our second challenge is that the thin layers of these visible dyes, so even if we do find dyes that are visibly opaque but infrared transparent, they don't create enough contrast for pattern detection. And our solution to this is to use phosphorescence. So what phosphorescence allows us to do is to have these particles, these phosphorescent particles, absorb higher energy ultraviolet light, and it actually emits visible light within the visible spectrum, so the RGB camera can sense it. And because it's activated by this really high energy light, it doesn't absorb this infrared light that comes from the depth camera, so we get the proximity and the tactile. So to fabricate the soft membrane, we use a layering approach. It's made of 3 layers. The first layer is a base silicone elastomer. We use EcoFlex 30, and it's mixed with this visibly opaque and infrared transmissive dye. Then in layer 2, we pattern the dots with a stencil and phosphorescent ink. And in layer 3, we seal it with a layer of EcoFlex, which kind of evens out the protrusions from the dot layer, and also makes the surface slightly more matte, so that we get less of the reflections from the internal LEDs. And this process is pretty simple. It takes about 30 minutes to fabricate a membrane. So here's the entire system, which we integrated into an end effector. So you can see the selectively transmissive soft membrane here. We have some internal ultraviolet LEDs. We also have an air pressure sensor. And for our cameras, we chose the Intel RealSense L515, which has both a depth camera that operates in the infrared spectrum, as well as an RGB camera. And we're sampling all these sensors at 30 hertz, so it's synchronous sampling. We're sampling the air pressure sensor at 30 hertz, the depth camera at 30 frames per second, and the RGB camera at 30 frames per second as well. Our sensing surface is 96 by 54 millimeters. And again, we integrate this into an end effector, and we mount it on a robot arm. So for tactile sensing, we have two methods to do contact detection. The first is with optical flow tracking by tracking the dots. So the dots move as the membrane deforms, and you can measure that deformation to get kind of an idea of, or you can measure that motion to get an idea of deformation. And the second way is with the internal air pressure. And so this is pretty intuitive. You would expect the air pressure to increase when an object comes into contact with it. And you can see how both of those plots on the right show how the flow velocity, which is kind of sums the entire motion of the dots over the frame, as well as the air pressure increases. So here's a small demo of optical flow tracking. I'm just pressing a Rubik's Cube into the surface. And you can see how the direction of the arrows gives you an idea of the direction of shear. And the magnitude of the deformation is kind of measured by the length of the arrows. And this is a pretty standard Visuotactile sensing algorithm that's implemented. So for the proximity depth sensing evaluation, so even though we tried to make the membrane as transmissive as possible to infrared light, we still have some effects from the dots. So you can see here in this point cloud, we're actually looking at a flat surface, but it looks pretty bumpy. But however, these dots aren't occluding the proximity depth. It just makes the dots appear slightly closer, usually only around 2 millimeters. But because we have these two simultaneous and synchronous frames, we're able to align the frames and identify where the dots are located and correct for it. So we apply a local smoothing algorithm, and we have a much smoother, more representative point cloud of what we're actually looking at. And then we also evaluated the depth camera data, which is from away from the surface, from 10 millimeters to 100 millimeters in this plot right here. And we have an R-squared fit of 0.725 after the dot correction has been applied. So to evaluate the spatial accuracy of our sensor, we place some common items on the sensor. So you can look at the sensor outputs here. The middle row gives us the proximity depth information. The bottom row gives us our tactile RGB data. And so we looked at the breadboard, the shark torpedo, nail polish, and also the Rubik's Cube. And we looked at the significant dimensions of each object, so like the length and width and diameter. And we found an average error of around 4.3%. So finally, I'll show some demos. So we mounted the sensor on a UR10 robot arm, and we demonstrated in 3 open-loop tasks, which are approaching contact, catching, and throwing. And I chose each of these 3 tasks because they can be segmented into 3 different stages. One stage being pre-contact, another stage being during contact, and the last stage being post-contact, which is where the modalities of tactile and proximity would be helpful. So the first one, I'll start with approaching contact. And the videos go kind of fast, so I'll run through it a couple times. But essentially, you can see the bottle, the outline of the bottle, even though it's not in contact with the tactile sensor. So you see it approaching in the proximity depth map, and you also see it right here. And then you can also compare what the proximity depth looks like compared to the ground truth, which is the pose from the robot arm end effector, and also how the total flow velocity and the internal air pressure increases and decreases with contact. Okay, and now we have catching, which I've slowed down to 0.12x speed. And so the nice thing about this is you can actually see the Rubik's Cube in the proximity depth map before it even comes into frame in the original, the camera that I'm using to film the demo. And you also see the response from the tactile sensor. So we catch about 13 frames of the proximity depth before it comes into contact. Finally, we have throwing, which I slowed down to 0.25x speed, which also goes pretty fast. And I think the interesting thing about this is that you can see the motions of this object in the hand of the sensor almost, which would be kind of hard to track with an external camera because it goes so fast. And we also catch a couple frames of it after it leaves the sensing surface in the proximity depth map. So we get about 6 frames, even though it's moving at 1.5 meters per second by the time it leaves. So in conclusion, we presented this selectively transmissive soft membrane and phosphorescent dot pattern that enables the both proximity depth and visuotactile sensing modalities. We also showed a quantitative evaluation of the proximity depth and tactile sensing. And we showed how the sensor can be integrated into an end effector and demonstrated on a robot arm with approaching contact, catching, and throwing. So for future work, this is probably the one I'm most excited about, which is sensor fusion for contact patches of deformable objects. So to the best of my knowledge, this sensor is the first time that we can have high spatial resolution and direct shape sensing, so we get a point cloud of the object at the contact interface. So before, you would have to kind of interpret these deformations from 2 deformable surfaces, and that's pretty tricky, but this time we actually can directly sense deformable materials at that contact interface. We're also looking into building up force torque estimations, and integration with soft fingers for in-hand manipulation. So the large sensing surface of our sensor, which again is 96 by 54 millimeters, allows for the sensor to act as a sensorized palm. And with that, I would like to thank my co-authors, Greg Campbell, Dr. James Pikul, and Dr. Mark Yim, for their contributions to this work. Couldn't have done it without them. I would also like to thank my sponsors from NSF. And I'd like to thank you for listening to me today, and I'd be happy to take any questions now.
Thanks for the very interesting talk. Yo Young Hong also thanks you for the great work and asks the question whether it's also possible to recover color information using the proximity sensor.
Yeah, that's a really good question. So actually, because the proximity sensing depends on time of flight, which is basically how objects bounce back or reflect infrared light, then we do actually have a noticeable difference between darker colors and lighter colors. So lighter colors will reflect the infrared light more, while the black colors will absorb the infrared light a little more. So that is something that I haven't really investigated, but that would be pretty interesting. Thank you for the question.
Yep, thank you. And we have a question there in the audience.
Well, pretty cool indeed. Congratulations. But I was wondering what happened if the object that you're trying to sense emits some kind of heat, or it has some, I don't know, is cold or warm or something like that. will that affect your sensor?
I'm not totally, my intuition right now is probably not, because because we're only sensing the emitted infrared light from the depth camera. So it's not taking in other like sources of infrared light as much, because it has a really nice, basically the depth camera emits at a certain modulation frequency, and we're only detecting that infrared light emitted by the depth camera. So I don't think radiation or anything from other objects would affect the sensing.
Thanks.
Okay, we are short on time. I take one more question. What are the size limitations of this method, both large and small?
Yeah, that's a good question. So actually, kind of like the con of using an off-the-shelf sensor is that we're limited to what is available from off-the-shelf. So, but really the sensing surface is limited by the field of view of the cameras. So we want to capture the surfaces or the interface where both of the field of views overlap. So we do have a minimum sensing range, which I've kind of pushed to, as far as I could get it here, to around 50 millimeters, but on paper, it should be 100 millimeters, but so we're kind of limited more in the camera manufacturers rather than like our sensing mechanism.
Thank you very much. There are more questions, but I think we have to take those offline. So
Okay.
Thank you very much again. Thanks.
Thank you so much.
Thank you.